So when we say expand, we're saying multiply it out, which means distributive property, which means getting rid of parentheses here. So if I'm going to do that, I need to multiply through. Now, in the case of where I do a binomial times a binomial, I have to multiply every term in the first parentheses by every term in the second parentheses. So that means I'm going to be doing x times x, which is going to give me the x squared. Then I'm going to have to be doing the x times the minus 7, which is minus 7x. And then we're going to do it with the minus 8. So minus 8 times x is minus 8x. And then finally, I'm going to do the negative 8 times the negative 7, which gives me a positive 56. The last thing we do is go ahead and combine the like terms here. The only like terms we have are the x's in the middle, the minus 7x and the minus 8x. Negative 7 minus 8 is negative 15. So that's a negative 15x plus 56. That is then your final answer. That's what we're looking for. So we're going to now distribute this 7x cubed into the parentheses here. In this case, there's just the one term in the first part, but that will have to go ahead and distribute to all three inside the parentheses. So then, separate that out. When I do the 7x cubed times the x to the fifth, notice there's no number with the x to the fifth here. So the 7 is just going to stay as 7. And then I have to multiply x cubed times x to the fifth. And hopefully, you just remember a rule there. You know what to do with the 3 and the 5 to get that. But if you're not sure what this exponent is going to be, you can actually visualize it, because I'm going to be doing x cubed, which is x times itself 3 times x to the fifth, which is 5x's all multiplied out together. Well, notice we just have a total of 8 x's all multiplied out together, which means that this is 7x to the 8th. So what was the rule that we might have known? When you multiply the x's, you add their exponents. But again, if you don't remember that particular rule, rather than guessing at which rule it is at any given time, you can actually kind of figure out what it would be by writing them out, or visualizing even what would happen if we wrote them all out. All right, now I'm going to multiply the 7x cubed by the 4x. So I multiply the 7 by the 4. They're both positive, so this gives me a positive 28. And then I have x cubed times x. What exponent is on this x, even though it's not written in there? 1. And so if I do the 3 plus the 1, that gives me x to the 4th. It's a grand total of 4 x's being multiplied together there. All right, and then next up, we're doing 7 times the minus 9. So that's going to give me a negative 63. Now in this last term, there are no x's right now. So when I multiply the x cubed into it, it's just going to stay an x cubed. That then is the final answer that we get for that one. And one thing that I'll sometimes see as I walk around the room at this point is I'll see some of you wrote down the original problems, good, but then you're just not going any further than that. If that's because you have no idea where to go, okay, that can happen. But usually you have some idea, like, well, I think I know at least this much or something like that. At least try those things. At least start working through them, even if you're not sure, because you'll be amazed at how much you'll actually discover that you do know. And when you do hit that wall, you'll understand where that wall is, which helps you to then learn how to get past it. Rather than just trying to remember the entire process as I go through it, you are hopefully focusing on either just checking your work or saying, okay, well, I got that part, but okay, now that's the bit I needed. So you don't have to try to remember everything that we go through all at once. All right, so we're factoring. We're going to go through this first one. And the first thing I always do with these is I just look at the numbers out front. In this case, the 12, the 18, and the 10. And look to see what can I divide out of all three of those. And it looks to me like in this case, that's just going to be 2. So the first number that I'm going to be pulling out of this is just going to be a 2. But you'll notice I also have x's in every term. I have x to the 7th, x to the 5th, and x to the 4th. How many x's can I pull out of every term? Yep, 4. Because, like for instance, this x to the 5th, I could pull 5 x's out of the 7 that I have here, but I can't pull 5 out of the 4 I have here. So basically what I'm doing is I'm looking to see what's the fewest number of x's in all of my terms. And so that's the fourth. So I'm going to say that I'm going to factor out 2x to the fourth power. Now, just like when we did distributive property in those last couple, I multiplied whatever outside into the parentheses. In this case, I'm dividing instead of multiplying because I'm going backwards. So I'm going to do the 12x to the 7th divided by the 2x to the 4th. 12 divided by 2, of course, is 6. And then I do the x to the 7th divided by x to the 4th. Well, again, a little bit of visualization. How do I do that? Well, x to the 7th means 7 x's all multiplied out together. And if that's going to be all over, that is divided by x to the 4th, I'm looking at something like that if I write it out the long way. I could then actually start canceling out pairs of x's that I see appearing on both the top and the bottom. And you notice what I'm left with. I'm left with 3 x's only on the top. And so that means that it is 6x to the 3rd power. What's the rule, in case you just like knowing the rule? You subtract the exponents. So when you divide the x's, you're subtracting their exponents. But of course, you can always visualize it that way in order to be able to see what's going on. All right, let's go ahead and just run through the rest of that now. The minus stays a minus. 18 divided by 2 is 9. If I pull 4 x's out of the 5 that I have here, I'm left with just 1x, which means I'm just going to write it as x. Now, if you wrote it as x to the power of 1, that is technically correct, but it's just a little bit better style, a little bit smoother, a little bit more efficient and simplified to just write that as x. All right, and then finally, the plus stays a plus. 10 divided by 2 is 5, and x to the 4th divided by x to the 4th is 1. Not x to the 1, but just 1. There's no more x's left in that last term, and so it's just a 5. And that's that first one done. All right, now on to the second. We again look to see what can I divide out of every single term, and I start with the numbers. So as I look at 20, 15, and 5, they're all divisible by 5. So I start by pulling a 5 out front, and then I look to see how many x's can I pull out of every term. The fewest number of x's in any of the terms is the last one, the x squared. Yes, it is often the case that it will be the last one. That's a great place to start looking. Just realize there's no rule that says that it has to be the last one. So we're going to pull out 5x squared, and then we just do our division. So 20 divided by 5 is 4. I'm taking 2 of the x's out of the 5 here, which leaves me with x cubed. Plus stays a plus. 15 divided by 5, 3. I'm pulling 2 x's out of the x to the 4th, which leaves 2 behind, so that's going to be an x squared. Plus 5 divided by 5 is 1. X squared divided by x squared is also 1, not x to the 1, but just 1. And so the x's are all gone from that last term. We're done. The biggest trick with this one is knowing and remembering that we do have to have that 1 there. It can be tempting to just leave it off because we factored out the whole 5x to the 4th that we started with, but it does still leave a 1, because of course if I was multiplying this back in, I would have to actually multiply it into something in order for it to still give me that. The next thing we're doing is we are going to be taking some formal notes on something brand new. When we take notes in here, I suggest you keep all of your notes all in one area. Like pick a place now, like the very front of your notebook, or you start at the back. Just make it someplace where when you need to go look up a formula, you know exactly where to find it and don't have to flip through page after page after page in your journal until you happen to find the right spot where we did it, which often is a tough task by the time we fill in a bunch of examples and things around it. And so in that special place in your notes, you're going to be adding this information about logarithms. Copy everything just as you see it, and then we'll explain some of what you're seeing. All right, now today we are introducing the concept of logarithms, but we're doing this in a somewhat out of order way, because today what we're going to be focusing on is just how we can see that these two forms, this and this, are equivalent, and how I can actually just rewrite one as the other and have it mean the same thing. But we're not going to be using the logarithms for everything that they can do yet, because there's a couple different layers to logarithms that ending up potentially at least causing us to stumble a little bit. And if we take them kind of over time, we eliminate some of those stumbles. One of the things is just how do we switch between the forms, which is what we're working on now. In the not too distant future, we'll then see how to actually do calculations with logarithms. So we'll be learning how to actually take something that looks like this and plug it into your calculator to get an answer. Notice that's not what we're doing today. So we aren't even necessarily calculating the logarithms yet. Just realize that it is something we can calculate. Once we've done both of those pieces, seen how we can rewrite these as each other, and then calculated a logarithm, we will then be using these logarithms to solve exponential equations. And so we're going to be using it to solve something that looks like this. Or to give you something a little bit more concrete, imagine if I told you 2 to the power of what equals 8. Now you can do that in your head, I hope, because we can figure out, okay, 2 to the power of what would be 8? 2 times 2 is 4, times another 2 is 8, therefore the answer would be 3. But what if 2 to the power of x equaled 3? We're not going to know that off the top of our head. But there is just one value of x that gives us that value. It's some decimal. And what the logarithms do is they allow us to actually be able to calculate what that decimal is. It's just that we aren't going to do that calculation quite yet, but I mention it so that you have some context about why you're learning this piece that we are learning about today. Because we can only solve that if we know how to turn my exponential into a logarithm. So that's the first step in getting there. Now you notice a little bit of detail down below there. We read that log with the subscript b, y. We read that as log base b of y. Now, remembering how to read that is also going to help you know how to rewrite it, because if I take a look at my exponential over here, in that case b in the exponential is also called the base of our exponential. The base is whatever's raised to the power, and in a logarithm, that is also your base. That subscript is the base. Notice I'm calling it a subscript. That just means that it is written smaller and lower. It's kind of like an exponent, you know, where you write it smaller and higher. The b, you write it smaller and lower. So next up, we see how we're going to use these and actually put this transition into practice. So we're going to do these 4 problems together. Before we actually start working them through, though, go ahead and write down the 4 problems. That way you aren't trying to just write it down instead of being able to listen to our process. And then we'll go through them. All right, so the first 2, we're writing the exponential as a logarithm. And this is really the most useful thing for you to be able to do, because we use logarithms to solve for exponentials. And so by being able to do this, once we add a few other little pieces down the road, you'll be able to then calculate some of these values. So let's go and take a look at that first one. 5 to the x equals 10. It's a full equation. It has to have the equal sign and everything in there in order for us to be able to do this. Now I know I'm writing it as a logarithm, so the very first thing I'm going to write down is I'm going to write log. All right. The next thing that has to go in there is the base of my logarithm. Now, we're just getting to know how to do this. So what I would do is I would look up here and I'd say, okay, I'm trying to figure out what b is. So notice over here. Notice where the b is in the exponential equation. It's whatever's raised to the power. That's our base. So in this case then, that must be the 5. So I'm going to go over and put my base of my logarithm in as 5. The next thing I'm going to have to write here for my logarithm is what in the original formula up above there is called y. There's nothing magical about calling it y. That's just a placeholder so that we know where to look for it in the other equation. Notice it's what it's equal to. One of the ways that I always remember how to make this transition is that I remember that log always equals the exponent. Well, the exponent is the x. And so the y must be the other one. Maybe that'll help. We'll see. But in this case, oops, almost marked the wrong thing. In this case, this is my y value. And so that 10 is what has to follow the 5 here. So we have log base 5 of 10. And then notice the next thing in my formula up there is the equal sign. So I put in the equals, and then it equals x. So log always equals the exponent. Kind of jumped the gun and mentioned that earlier, but that's how I remember this part, is that log always equals the exponent. And so in this case, my exponent is called x. So this whole thing, this whole log base 5 of 10 is going to equal x. And that's it. That is done now. And that's what we're going for. Now, a little side note on this. After we've practiced doing these sorts of conversions for a little while and we've gotten comfortable with it, then we'll see how we can then go and calculate something that looks like that and actually figure out what that x would be. So yes, we will get there, just we're not going to do it all at once because then there's just way too many new moving parts and it can be hard to keep track of it all. All right, the next one, h to the m equals w. It's going to be the same basic idea, just instead of some numbers, they're all letters. First thing I write is I write the log. Next up, my base. Take a moment, think about what do you expect that base to be, which letter is it, and you hopefully are seeing that up in our original formulas up there, it's the b. It's the base. The base of my exponential is whatever is raised to the power. In this case, that is h. So this is log base h of, now again, think about what do you expect this letter to be. So you're practicing. In our formula up above there, that's the y. So you can see that in our formula over here, that's the w. So it's going to be log base h of w equals, well, process of elimination can probably tell you what that other one is, right? But I can also remember it because I know that log equals the exponent, and so it has to equal m. All right. On the bottom two now, we're doing the exact same thing, but we're doing it backwards. So I'm going to be writing an exponential next. Now notice that means I'm not starting by writing log. I have the log already. I'm trying to get rid of it by rewriting this in exponential form. So the very first thing I want to do is I want to grab that b value. Well, the b, remember, is the base. The base of my exponential, the base of my logarithm here is 2. So the first number I'm going to put in there is 2. And it's going to be 2 to the power of something. Well, remember, log always equals the exponent, right? So this logarithm is equal to 4. Therefore, 4 must be my exponent. And so we're going to have 2 to the power of 4 equals, well, process of elimination, again, can probably tell you what that last one is. But if not, you could always look up at the formula here, and you could see that what we're looking for is the y, and that is what we're taking the logarithm of. In this case, that is the x. And so 2 to the power of 4 equals x, which, by the way, notice, means that you actually could figure out what x would equal in this problem. Because by writing it as an exponential, we saw it was 2 to the 4th, which happens to equal 16. So x happens to equal 16 here. Not that you have to find that, because we're just writing it as an exponential, but I want you to see kind of how we can manipulate these to get some answers. All right, last one there. Again, we're going to start by figuring out what is the base of our exponential going to be. Take a moment. Which letter is that going to be? The base is the base of the logarithm, which is n. Next thing is going to be the exponent. N to the power of what? Again, look ahead. Think about which letter is that going to be. Since log always equals the exponent, my exponent must be c. And finally, yeah, process of elimination would tell us that the last one is a, but again, you could also look up here and see that that's the y value. It's whatever's inside of the logarithm there, to be able to know what that is.